Hey, what's up, guys? Just putting a quick video together, run through a PowerPoint, a little intro to atoms for some of us that needed a little bit of extra help when we're going through those videos. So let's take a look. The idea of matter, right? Last week we talked about living things. We talked about how living things are made of cells. And then we also talked about how there's non-living things too, right? And then we said, well, what the heck are non-living things made out of? So last week we came up with non-living things are made of atoms and that atoms are smaller than cells. This picture is a pretty good representation of a model of an atom. We've got some protons and neutrons in the nucleus, and we've got those little things buzzing around the outside. Those are our electrons. We're going to go through this pretty quick. You're welcome to pause. You're welcome to go back, do whatever you need to do. So this video is here for you. Matter is anything that has mass and takes up space. So anything that is stuff, it's matter, right? I say matter is stuff. So anything that you could say, yes, that is made of stuff, that's matter. Anything you can knock on, hit, whatever, that is stuff. So the example is a brick, a desk, a pencil, air. That's one that people don't usually get, right? We have air, it's taking up space. We don't see it necessarily, but it is there, it takes up space. All right, so another representation, something you guys are going to need to be able to do this year is to model an atom or to represent an atom. I know we don't have a great idea of what they are yet, but that right there is a pretty good picture. We've got protons and neutrons. Protons are positive, right? So pro is positive. Neutrons are neutral, right? And then electrons are negative. So why do those electrons keep flying around the outside without just flying off into outer space? Well, the protons are positive and the electrons are negative, and we know positives and negatives attract, so there we go. So atoms, let's see what that was. Atoms, smallest unit that we have. There are parts of an atom, right? So like the protons, neutrons, electrons, we've got other things too. We've got quarks we could talk about. In college classes, we could go on and on. There are parts, but atoms are the smallest building block of non-living things, right? So like when we're thinking about this, I think like if the world was Legos, right? Like atoms are those individual Legos. So protons, neutrons, electrons, there are other pieces that are way smaller that build those up, but that's good enough for us. And then one of the models we use, we can compare it to the solar system, right? Because everything's going around the sun. We could say that the planets are like the electrons, the sun would be the nucleus. All right, so talking about how small these things are, I'm not going to read through all of that. You guys are welcome to pause this. You're welcome to pause this and take a look, go through that. When it says at the bottom, that's one that's cool to look at. It says it would take you around 500 years to count the number of atoms in 1 grain of salt, right? So you think like 1 grain of salt, you can see that, okay? So if you can see it, it's way bigger than an atom. If you scratch your face, right, you scratch your cheek a little bit, you don't see your cells, right, in your fingers, but our cells have atoms in them, right? So atoms have to build non-living things. So we're thinking about that, like you have a Gatorade, right? The electrolytes, right? You're basically just putting salt into your body. That's sodium. Your cells take in that sodium. There's atoms within your cells. So if you're thinking like that, it makes it seem like an atom is so much bigger or so much smaller than a cell, and it's true, right? We could fit 1 trillion atoms into a cell. So thinking about cells in our body, you scratch your cheeks, you don't see those things on your fingers, right? Our skin, everything's made of cells. Atoms are in there, and atoms are so much smaller than cells. All right, so this is something you guys could do. Do this at home, right? It's kind of a fun activity to see if you actually can. Try to cut a strip of, it says 11 inch, that's just like a normal standard piece of paper. You're going to keep cutting it in half, right? Keep making your cuts the same direction. Keep going sideways, sideways, sideways. If it gets too long and awkward to cut, you can cut some of the flap off, that's fine. But try to see how many times you can cut it. See if we can get it down to the size of an atom. Spoiler alert, you can't. You would need to cut it 31 times. Okay, so thinking about that, you may have gotten, what, like 7 or 8 cuts? Okay, so you're a fraction of the way. to how small an atom is, and your paper is already really small. So taking a look at protons, they're in our nucleus. They are positive. So starting to get into some periodic table stuff. The number of protons is equal to the atomic number of the atom. So we're thinking like hydrogen is the atomic number 1. Helium is the atomic number 2. Okay, that means hydrogen has 1 proton. Helium has 2 protons. Okay, protons are a little bit bigger. They do contribute to the mass. Okay, and they're equal to the number of electrons. Okay, so remember that positive and negative balance each other, right? So if we have 3 positives, we need 3 negatives. Now, eventually we can talk about isotopes and that, or right, we could talk about positively or negatively charged atoms where we could give an extra electron, take an electron away. But that's into high school when we talk about atomic bonding. So for right now, we can think we need the same number of negatives as we need positives because we need to balance it out. Neutrons, no electrical charge. They are neutral. They're a little bit bigger as well, so they also contribute to the atomic mass. So protons plus neutrons is going to give us that atomic mass. Electrons, they're negatively charged. They are found outside. So they're like the planets flying around the sun. We call it the electron cloud because these things are flying all over the place. There are a few different models of this that we could represent, but basically we create this electron shell or this electron cloud where all of these things are flying around so quickly, and they're stacked into different, we call them valence shells. It's a little bit beyond where we need to be in 7th grade. We'll leave that for high school chemistry. But basically each shell can only hold a certain number of electrons, right? So like the first one can hold 2. So like hydrogen and helium, they only need that first electron shell because hydrogen has 1 electron, helium has 2. We start to move up a little bit, and then we go on to the next shell, and that would be 8. And then we call the outermost shell the valence shell. That's kind of just some vocabulary for us, and that is really important when it comes to bonding and atomic bonding, covalent bonds, ionic bonds. Okay, so this is an example of a hydrogen atom. So you say, well, it doesn't have a neutron. That's weird. Well, if we check it out, the mass is also 1, right? So we have 1 proton. The atomic number is 1. That tells us there's 1 proton. And the atomic mass is right around 1, right? So electrons are very small. They're basically negligible when it comes to the mass. But if this atomic mass is only 1, then we know there can't be a neutron in there. All right, so we see that. We see it flying around. Get a little optical illusion where it looks like there's more than 1. Boom. All right, oxygen. Oxygen's atomic number is 8. Okay, so if we looked in the periodic table, you guys have that activity where you're doing the mystery matching of the elements. Oxygen would be number 8 on the periodic table. It has 8 protons. It has 8 neutrons. It has 8 electrons. An isotope of oxygen, we don't need to worry about that, could have a little bit different numbers. But oxygen in its natural form, boom, we have it right there with 8. So we see there's 2 electrons in that first shell, and then there's 6 left to go to the next shell. The atomic number for oxygen is 8. The atomic mass is right around 16. So 8 plus 8 is 16. That gives you the atomic mass. See them flying around. All right, sodium gets a little bit bigger, right? So we've got 11 protons, 12 neutrons, and 11 electrons. So with those 11 electrons, we're going to have 2 in the first shell, 8 in the second shell, and then 1 in that last shell, right? Because it goes 2, 8, and then we grow from there. It has 12 neutrons. If we looked at the atomic mass, it would be right around 23. So that's how you would know there's 12 neutrons. If I told you sodium's atomic number was 11, and it had a mass of 23, you would need to know that 23 minus 11 is 12. And that's all there is to figure that out. So the atom's center, that's our nucleus. Okay? We also call it a nucleus of a cell, so it's kind of nice for you. It just means the center. Electrons are not a part of this center. They go around the outside. So we could talk about quarks, right? They make up protons and neutrons. Talked about that earlier. That's well beyond where we need to be for 7th grade. But if you're interested, look it up. Some interesting stuff. You could learn about what we're finding out about atoms. We're actually finding new particles within atoms semi-regularly. The Hadron Collider out in, where is that? Switzerland, I believe. They just take protons and neutrons, they smash them into each other, and they just try to blast them apart and see what happens. All right, so taking a look, that's what I was saying. The mass of electrons is negligible. It would take 1,839 to make one neutron, so we kind of just don't really worry about those as a mass. Obviously, we will if you were like a nuclear physicist or something, but for 7th grade science, we're okay. One neutron is about one proton. One neutron is a little bit heavier than one proton. Has a little bit more mass, I should say. That's a good point to talk about. What's the difference between mass and weight, right? Mass is how much matter you have, right? How much stuff is in my body. Weight is how hard that stuff is pulled down onto Earth with gravity, right? So if I went to the moon, my mass won't change. There's still this stuff is still inside of me. I still have the same number of atoms, right? But my weight would change because Earth's gravity is stronger than the moon's, so Earth is pulling me down more. So think I'm standing on a scale, right? That scale tells me my weight. It's that mass with the gravity pulling down. So my mass won't change, but if I went out to outer space, obviously my weight on the scale would change. All right, so more kind of just looking sizes of these things, talking about how much smaller it gets from here. And we're already saying that an atom is so tiny, right? We could fit 1 trillion atoms into a cell. So when we're getting down to like the quarks and the electrons, these are really, really, really small. Atomic number, number of protons, we already talked about that. The mass number, it's protons and neutrons. Atomic mass units, AMU. So looking at this, what would be the mass of this? Well, we count it. There's 3 protons, there's 4 neutrons. That would be an atomic mass of 7 AMUs. 3 plus 4 is 7. What did we not account for? Why did we not account for the electrons? Because they're tiny. There'd need to be what? Like close to 2,000 of them, and there's not. All right, building atoms. You guys at home or on a piece of paper, this is what I would like you to do, or preferably not on a piece of paper, right? Because you can't give it to me. But you could do this in like the Paint app. You could do it in Word with shapes, and then go ahead and attach that as your work. Okay, so I want you to make one of carbon, one of beryllium, one of oxygen, one of lithium, and one of sodium. Okay, I'm going to say since there are 5, I'm going to ask that you make 3 of them for me. Okay, so remember protons and neutrons go in the middle, electrons go on the outside. I want you to draw 3 of those, either in Paint, on Word, whatever other program you could come up with, and then just go ahead and use that snippet tool. Send it to me, and that'll be your work for this assignment. This website also works if they are active. I'm not sure if they still are active. You could do this and use the snippet tool as well. All right, so looking at some forces of atoms, we're going to kind of blow through this because this is well beyond what we need to do. But anything with mass has gravity. Okay, so like my cell phone's sitting here. My cell phone has gravity. Okay. Things are not attracted to my cell phone sitting right here because Earth's gravity is way stronger, right? So like we are being pulled to Earth. But in outer space where there's not gravity and vast voids of space, if you throw a handful of rice out there, over time these things would start to meet up and to be attracted towards each other, right? Because of that gravity. And that's how planets were formed back in the day. We had space dust. Space dust gets pulled together, packed together. After millions, trillions of years, we end up with all this good stuff, right? We got billions of years that Earth's been around, so we've got plenty of time for dust to become big rocks. All right, we're going to blow through these, almost at my 15-minute limit for the video. I've told you guys I won't go longer than 15 minutes, so if you want to go through and pause these, strong force, weak force, any of this stuff, this is all high school physics. Isotopes, boom, you guys can learn about this in chemistry and physics. Atomic mass, we already talked about that. Here's a quick run through. You can pause it if you need. Ions, Boom. All right. Peace out, dudes.